Hi. And I thought I would explain how I got into this whole train of thought as the hairstylist and, looking at Michio Kaku's Quantum Supremacy. And I came across Feynman's path integration. All right. So that kind of got me thinking, not to be confused with line integral. And path integral is quite complicated, but it just means that a quantum particle traveling from path xa at time ta to the point xb at in time tb, at reaching xb at time tb is, we remember, uncertainty principle, etc. Quantum particles, momentum, cannot explain the position and momentum at the same time. So it becomes difficult. So you need to go through Feynman's path integral to actually explain. There's a handsome guy who's whose video you should watch, but he said he's derived the whole path integral, the, with the Hamiltonians and what else? Hamiltonians and whatever is required, Lagrangians and Hamiltonians, Lagrangians, and what have you. So he is worth watching though. Give him one view from you and one more view from me. All right. I'm going to watch him. Oh man, but no, I'm never going to see him. But he's a professor. We have professors who are very handsome in the Department of Chemical Engineering in the University of Toronto, and but they're very, very strict. This man looked okay, I thought, but who knows? Anyways, back to focused. All right, let's say focused. Coming back, line integral will not explain path integral. So, anyways, path integral, etc. It goes on to explain many things. The quantum particles moving around and traveling in time, etc. So, and a good exercise would be to explain the electron jump. Remember, it goes from one orbit to the other orbit for the reaction to take place in chemical elements. Or chemical compounds of two elements with a third element. Electron jump through Feynman's path integral point xa to xb at time ta and reaching xb at time tb could be explained through Feynman's path integral. So that would be a fascinating solution to pursue. But what came to me at that time was Einstein. All right, Einstein said in a streetcar, time is different from the observer who's waiting. So he's waiting for he or she or myself waiting for the streetcar, and then when the person in the streetcar moving away is 2 seconds ahead of me waiting in the maybe it was not the right streetcar, waiting for the uh, streetcar to come, right streetcar to come. So the person who got it he's 2 seconds ahead of the person who's waiting for the next street. So that's what Einstein said. Relativity, all right, theory of relativity. In relative to the person who's waiting there, he's 2 seconds ahead of time. So looking at this explanation through Feynman's diagrams, which is fourth dimension time, so space on the y-axis and time always on the x-axis. So time, so a particle moving through time is simultaneously moving through space. Right? All basics. So looking at an airplane and a ship. All right. So I'm standing on a ship, which is moving too. Ship is not stationary. All right. I'm not a but I'm a stationary observer. On the ship, I'm not moving. So I see the airplane flying above, and so the person on the airplane taking a flight from Toronto to Frankfurt is going to be how many seconds ahead? So that's a problem you should pursue. All right, assigning. I will also solve, and if required, I'll solve because I'll be submitting this video to the chair of the chemistry department, Professor Fornoon, and at the University of Toronto, and if he says, go ahead, Gayatri, solve. There I'm solving. All right. So how many seconds is the person on the airplane ahead? How many seconds? Or if you think logically, moving through space, he's moving faster through space, so he is ahead. So time, so space time continuum, so he is ahead. So relatively speaking, to the person on the ship can move as fast as the airplane. So it's the time moves relative to the person on the airplane. It moves slow. Times no, that's Einstein's theory of relativity. Einstein proved it, so I don't need to prove it. All right, no proving. All right, so anything else? What else could I look at? Well, train. Einstein's done this. Then Bertrand Russell in the ABC of the Relativity has dealt with this. So what else? What else could you think of? I mean, Andre de Grasse, he got the Order of Canada, Yeah, Canada's seven-time gold medalist, seven times medalist. He got the Order of Canada for doing philanthropic work and that sort of thing. Also, I mean, not just for running, sprint running. So he, is running, and I'm watching him, and um, on his watch, on his watch, and he's running. The time is moving faster, or it may be a fraction of a second faster. So gotta watch those watches, people. So on his watch, he's done the sprint faster than the people who were recording the time in the Olympics. That's a fascinating thought, isn't it? Well, you want to run really fast in the sprint? Take a blueberry gel made by UC Berkeley laboratories. So somebody says, I'm getting all confused. Laboratories, 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 laboratories. Hmm. This is somebody who's fresh off the boat, India. Yeah, they confuse issues. All right, I start losing it. It's not nice. People who listen to them a lot, they start getting confused. No, but people who have studied, born and brought up here, and who have gone through schooling here must be left alone. All right. So anyway, so UC Berkeley laboratories, UC Berkeley labs. We'll quit this whole conflict of pronunciation, and say that UC Berkeley labs makes it. You will do faster times than Andre de Grasse. All right, if you take this, you to walk up a 15 minutes. You're going to do faster times than Andre de Grasse. I gave up on sprinting because passers-by may have observed me and my wishes, which have never been granted to me. All right, so so goes to prove to you that people without wishes can solve Einstein theory of relativity. Please me. All right, signing out, Gayatri Sitaram. Thank you.